Hi, welcome back to this video. This is the fourth video in the topic reaction kinetic, which is under reaction rate. In this video, we will going to focus on the learning objective G, at where we need to using the following methods to determine the order of reaction. There are 4 methods that we need to know. These are the 4 methods to determine the order of reaction. First, we look at the unit of the rate constant. Second, we call initial rate method. Third is based on the graph concentration versus the time. And then the fourth is the graph method as well. But this time we need to focus on the linear graphs based on the integrated rate equation. The first method is known as depends on the unit of the rate constant. So how we determine the order of reaction? Basically, we use this formula. If we want to know the order of reaction, we have to use 1 minus the power of the concentration. So let's look at this example. The rate constant for the decomposition of a certain insecticide in water is 1.45 per year. So based on this rate constant, the unit for the molarity is to the power of 0. So means that 1 minus 0 equal to 1. This is first order reaction. Now let's proceed to the exercise, also applying the first method that we learned just now. For example, for the A, the decomposition of a compound A with the rate constant is 0.083 mole per decimeter cube per minute. So that means I can simplify this unit to molar per minute. So the power of the concentration here is represent 1. So I will use 1 minus 1, so equal to 0. So for the order of reaction for this decomposition of compound A is 0 order. Next, let's look at the question B. So the rate constant also given, which is 0.109 molar power to the negative 4 m per second. So 1 minus power for the concentration is negative 4, so it's equal to 5. So that means the order of the decomposition of HCOOH is 5th order. Second method is known as initial rate method. When you are given a table like this, and then if with a field of experiment, at least 3 experiments, then you know that you are going to use the initial rate method to determine the order of reaction. So here we need to determine the order of reaction, and then we need to find out what is the rate constant, and also we write down the rate law. So how are we going to start this question? Basically, we need to choose 2 experiments at where the concentration for one of the reactant is varies. So varies here is means different, while the concentration of others reactant need to be constant. Now let's choose 2 experiments at where one of the concentration of the reactant is varies, but the others will be constant. So for example, I can choose experiment 1 and I can compare with experiment 3, because in this case A is different, 0.1, 0.2 different, but the B 0.1, 0.1 are similar. So how we going to write down the working step? So you will say we will use, normally you want to use experiment 1 over experiment 3 also okay. Or you want 3 over 1 also okay. So normally to make it easy, we will look at the initial rate of reaction. 1.2 exponent negative 3 and 4.8 exponent negative 3. 4.8 is larger, so we will prefer using the experiment 3 divide with experiment 1. Then we will use the law method. Rate of the experiment 3 is 4.8 exponent negative 3 equal to K, and then concentration A. So concentration A for experiment 3 is 0.2 rise to the power of X, because we didn't know what is the order of reaction. And then concentration of B is 0.1 rise to the power of Y. Similar case as well, we didn't know the order of experiment. Then over experiment 1, which is 1.2 exponent negative 3 for the rate of reaction, and then over the K, concentration A at this time is 0.1 rise to the power of X, and 0.1 rise to the power of Y. So maybe in this case, condition here, the equal you need to put in the middle here a bit. Okay, then next, when we use the operation of division here, 4.8 over 1.2 exponent negative 3 will equal to 4. And then K and K can be cancelled out. Concentration 0.1 to the power of Y also can be cancelled out. 0.2 divided by 0.1 is 2 to the power of X. So from here that we know that 2 to the power of 2 equal to 2 to the power of X. So X will equal to 2. So order of reaction respect to A is second order. After determine the order of reaction to A, so now we're going to determine order for reactant B. So we have to choose two experiments at where the concentration of B is different. So in this case, we can choose experiment 1 and experiment 2. Because at the same time, the concentration A for both experiments are same, which we say here is constant. So again, when we compare the rate of reaction, 2.4 is larger than 1.2. So we're going to use experiment 2 divided by experiment 1. So the rate of reaction for experiment 2 is 2.4 exponent negative 3, and then equal to K concentration concentration of A for experiment 2 is 0.1 to the power of X, and then for B is 0.2 to the power of Y. Over experiment 1, 1.2 exponent negative 3 over K 0.1 to the power of X, and then for concentration of B also 0.1 power to Y. So 2.4 divided by 1.2, so it will equal to 2. K and K rate constant can be cancelled out. 0.1 to the power of X also can be cancelled out. So in this case, will be 2 to the power of Y. Then from here, we know that Y is equal to 1. So order of reaction respect to B is first order. So after determine the order of reaction, so now we're going to do the second part. We need to calculate the rate constant. So to keep in mind, when we need to calculate the rate constant, so we can choose either one of the experiment. Okay, let's say we choose experiment 1. So you will write down the initial means we apply the rate law. So rate of reaction equal to K concentration A to the power of 2 and concentration B to the power of 1. So now if you choose experiment 1, so the rate of reaction is 1.2 exponent negative 3. Value of rate constant unknown, so we replace with the symbol K, and then concentration A in experiment 1 is 0.1 rise to the power of 2, and then for B also 0.1 rise to the power of 1. So then from here, we know that k will equal to 1.2 exponent negative 3 divided by 0.1 exponent, 0.1 raised to the power of 3. Okay, then press the calculator, you will have the answer. So then how about the unit for the rate constant is need to be alert as well. So because the rate of reaction according to here is molar per second, and then over, because of the power of 3 here, so means that is molar cube. So molar and cube can be cancelled out, so we're left 2. So for this case, the unit of the rate constant you can simplify as molar to the power of negative 2 and then per second. Last part for this question, we need to write down the rate law. Okay, but basically we already write down the rate law when we want to calculate the rate constant. So after we determine the order of reaction, we will able to write the rate law. Like just now we say, rate of reaction equal to K, and then concentration A to the power of 2 and concentration B to the power of 1. So this is the rate law for this reaction. Let's proceed to tutorial question number 5. When you are given a table with a few experiments, so basically we know that we are going to apply the initial rate method. However, let's continue with the question. You are given a series of experiments, and then you need to determine the rate law. So we need to choose 2 experiments at where the concentration of P different, while concentration of Y is same, so that we can determine the order of reaction for P. Okay, so we can choose experiment 1 and 3 in this case, because the concentration of P are different, and then at the same time, the concentration of Y are similar. So then we compare, like just now we mentioned, 1.9 exponent negative 2 and 4.7 exponent negative 3. Exponent negative 2 is larger. So in this pair, we are going to use experiment 3 over experiment 1, which the rate of reaction for experiment 3 is 1.9 exponent negative 2 equal to K concentration P to the power of Y, and then Y to the power of okay, so if we didn't want to use the order because they are same unknown, P and Y, so maybe I can use the order of reaction is to the power of P and Q. So the concentration of P, like just now, we already decide we want to choose experiment 1. So then will be better, we directly substitute the value in, which is K, experiment 3 is 0.6 to the power of P, and then 0.75 to the power of Q, and then over 4.7 exponent negative 3 equal to K concentration for the P in experiment 1 is 0.15 to the power of P, while this one 0.75 to the power of Q. So this one can be cancelled out. K and K also can be cancelled out. So press the calculator. I think you will get like 4 equal to 4 to the power of P. So means that P equal to 1. Okay, proceed to the next experiment, where now we want to determine the order for the Y. So in this case, we are going to choose 2 experiments at where concentration of Y is different, while the concentration of P are same. So in this case, it's very obvious. We are going to use experiment 1 and 2. So again, experiment 2 value is larger. So we will use experiment 2 over experiment 1. 4.2 exponent negative 2 over 4.7 exponent negative 3. If you want to write like this also k over k. Then for experiment 2, the p is 0.15 to the power of p, and then for the experiment 1 also 0.15 to the power of p. For the concentration of y in this case is 2.25 to the power of q, and then 0.75 to the power of q. So k and k can be cancelled out. 0.15 over to the power of p also can be cancelled out. So end up when you do the calculation, you will notice that q is equal to 2. So then don't forget, the question is asked us to write the red law. So end up we can write down the rate of reaction is equal to k concentration p to the power of 1, and then concentration y to the power of 2. Okay, after discuss 2 examples, so now this is the terms that you are going to do this exercise. Please print screen and then try and answer it yourself. We will going to discuss during the tutorial time. Let's continue with the third method, which we base on the half-life, at where you are going to plot the graph concentration versus the time. So no matter it is 0, first or second order, okay, no matter it is 0, first or second order, we will notice that the curve is negative. Okay, however, if it is the 0 order, you will able to get a linear graph with the negative slope. Okay, and then for the first order, you will notice that the half-life will remain constant throughout the experiment, while for the second order, the half-life will have a 2 times longer compared to the previous one. Okay, because generally for the first order and also second order, we will get a curve, a negative slope with curve. Then how we are going to differentiate them? So try to look at here. Initial concentration is 1. So let's say the concentration become half, which is 0.5. So and then the time for here, this is the first half-life. So if 0.5, we want to make it to 0.25, which is the half. So this is the second half-life. So we will notice that the distance for the first half-life and distance for the second half-life are quite similar. So we say that first half-life is equal to second half-life. So that's why this is the first order reaction. Now let's proceed with the second order. Yes, same case. Initial is 1 molar. So when the concentration becomes half, means it is represent 0.5. So you will notice that this is the first half-life. So when the 0.5, the concentration of 0.5 molar become half, it will be 0.25. And then this is the half-life. So you will notice that the distance here is larger than the first half-life. This is second half-life. Okay, so basically we can say that second half-life is 2 times of the first half-life. If this is the case happen, so this reaction is considered as second order. Okay, let's proceed with one question. The following result were obtained from an experimental investigation on dissociation of dinitrogen peroxide at 45 degrees Celsius. So the time is given, and then at the same time the concentration also given. So in this question, they ask us to plot the graph, concentration versus time, and then determine the order of reaction. Like we discussed just now, if this is the condition given, so means that we are going to determine the half-life. So let's plot the graph, and then we need to find the red constant. Do keep in mind that. Based on the data that given in the previous slide, basically this is the graph that we are going to obtain. So now let's determine initial is around 176 exponent negative 4. Okay, so when the concentration become half, is go to around 88 exponent negative 4. So this is the 176, and then here is 88. Okay, so the time for taken from 176 to 88 is around 20 minutes. Okay, because the time here is in terms of minute, so we know that the first half-life is 20 minutes. Okay, then this one is settled. So time taken for the concentration 88 exponent negative 4 to become half is 44. So here is 44. So means that is from 20 minutes to the 40 minutes over here. So means that also this is the second half-life is equal to 20 minutes. Like we mentioned, if the first half-life and second half-life are same, so we can conclude that the order of reaction for this chemical reaction is first order. So let's look at the explanation here. The half-life for the reaction is constant and does not depend on the initial concentration. So therefore, the order of reaction is first order. Don't forget, the question also asks us to determine the rate constant. Since this is the first order, and then we already have the half-life value, so we can going to apply the formula for the half-life, which is ln 2 over k. So in this condition, we have the half-life, which is 20 minutes. And then ln 2, you can press the calculator, is equal to 0.693. Then the rate constant is unknown. So end up later, when you press the calculator, you will get the answer. And then the unit is in per minute. Now let's look at another example. Now in this question, they give us the data in the table, and then also like previous question, ask us to determine the order of reaction and also the rate constant. So the variable given is concentration and also the time, so that's why we can roughly plot the graph concentration versus the time. So initial concentration is 0.8, and then when the concentration 0.8 become half, means that it is 0.4. So that means from here, I can know that the first half-life is 12.5 minus 0. So first half-life is equal to 12.5 minutes. Okay, so sometimes, let's say if the question didn't let us know need to plot the graph, we also can roughly predict like this lah. Okay, so what about the second half-life? So now the concentration is 0.4. When the concentration becomes half, means that it is 0.2. So from here, the time taken is from 37.5 minus 12.5, which is 25 minutes, right? So this 25 minutes basically is referred to the second half-life. So when we compare the first half-life and also the first, I suppose this is the first half-life is 12.5 minutes. Okay, so now we try to compare. The first half-life is 12 minutes. The second half-life is 25 minutes. Like we mentioned previously, second half-life is equal to 2 times of the first half-life. So end up, we know that the order of reaction is second order. So this is another way. If we didn't plot the graph or the question didn't ask us to plot the graph, we also can roughly predict the order of reaction just based on the data given. The fourth method that going to help us to determine the order of reaction is we need to plot the linear graph based on the integrated rate law. So in the previous video, we already learned the integrated rate law for 0, first and also second order. So zero order is concentration A equal to initial concentration A minus KT. So from here we know that the y-axis is referred to concentration A, and then the initial concentration is C, and then the time is the X, and the K is the rate constant. So for the first order is ln concentration A equal to ln initial concentration A minus KT. While for the second order, the integrated rate law is 1 over concentration A equal to 1 over initial concentration A, and then plus KT. So that is why here is positive slope. Example, the data listed below, given the concentration is 1 up to 0.25, and then you also given the time. Establish the order of reaction, and then you need to by graphical method. So that means here you have two graphs can be drawn. Either is concentration versus time, or you can directly plot the integrated rate law. I mean the linear graph based on the integrated rate law. Next, the question asks us to determine the rate constant. So as we know, if we plot the graph integrated rate law, then it will be easier for us to determine the rate constant, because the rate constant always refers to the gradient of the graph. Okay, so in this case, maybe we will prefer this method, plot the graph, integrate linear graph for integrated rate law. But then we have 3 integrated rate law which refer to 0, first and second order respectively. Therefore, maybe we can use the cheat way like we learned just now. If the initial concentration is equal to 1, so when the concentration becomes half, so that means it will be 0.5. So that means it's around here. So we know that the time, maybe we just roughly take intermediate in between 5 and 10, which is 7.5 seconds. And then when 0.5 want to become half, the concentration will become 0.25. So from the time 7.5 to 25, so you can minus 25 minus 7.5, which is equal to around 18 something, roughly. Okay, so when we compare this one, this is the first half-life, and then this is the second half-life. Second half-life more than the first half-life, so basically I know that this is the second order. Okay, before I plot the graph, I already roughly have the idea. This is second order reaction. So to make it simple for you to determine the gradient later, since you already know that the integrated rate law for the second order is concentration A equal to initial concentration A plus KT. So means that you are going to plot this linear graph, and then you will show the positive slope. So if this happens, that means you can prove that it is second order. Then when you look for the gradient, you will find the rate constant. And then you also can determine the half-life using the half-life formula. Okay, so basically we already learned all the calculation and also the theory part in the topic 8.1. So now let's proceed to the tutorial question, at where sometimes it will combine all the knowledge that we learned in these 4 videos. So now let's proceed with the tutorial question number 6. The above reaction is first order, and then with the half-life 35 minutes. So first we will have to sketch the graph, concentration NO2 versus the time. So because this one is the first order, as we already know, you will get a negative slope graph, which is curve. Okay, so you can roughly draw like this, and then this one you will label concentration NO2, and then this one is the time. Since the half-life here given is in minutes, so maybe here times you can put the unit is minute. And then for the concentration, you can put a capital M, which represent molar per second. Okay, then second, calculate the rate constant, means that we need to know the K value. So again, because the question already let us know this is the first order, so and then you are given the half-life value, so we can use half-life for the half-life formula for the first order, which is half-life equal to ln 2 over K. So all the formula for the half-life for zeros, first and second order, and also integrated rate law, you must memorize. So half-life given, ln 2 also given. So press the calculator, you suppose will get the value of the K is equal to 0.0198. Due to this is the first order reaction, so the unit is per minute. Now let's proceed to number 3. Calculate the rate of reaction when concentration of NO2 is 0.06 molar per second. Because of only involve one concentration, so we can directly use the rate law at where rate equal to K concentration NO2 to the power of 1. Why we know it's power of 1? Because of here mentioned is first order. Again, the power in the rate law is represent the order of reaction, not the coefficient in the balanced chemical equation. So we didn't know the value of the rate of reaction, but the K value you already calculate in the part 2, so which is 0.0198. And then the concentration of NO2 given now here is 0.06 to the power of 1. So press the calculator, you will get the answer is 1.188 exponent negative 3 molar per second. So you can simplify molar per second. Question number 4. Determine the time required for 70% of the original NO2 decompose. So here we have two conditions. One is original 100%, and then after 75% decompose means that left original is 100%, and then left 25 or remain 25%. So in this case, we have two concentration, so we can use the integrated rate law at where ln concentration NO2 equal to ln initial concentration of NO2 minus KT. So because in this case, we didn't know the time, we know the rate constant, and then even though the concentration of the NO2 is not given, but then you can simplify that the initial concentration is 100, and then the concentration at the time or left is 25. So only have one unknown in this question, in this formula, so you will able to determine. Press the calculator, you will notice that the time is equal to 70 minutes. Okay, let's proceed to tutorial question number 7. The decomposition of A into its product is 0 order. The rate constant is 0.083 mole per decimeter cube per minute. And the initial concentration is 3.5 mole per decimeter. Calculate the concentration of A after 10 minutes. Okay, so basically when there is two concentration involved, we are going to use the integrated rate law. So you must remember the formula for the integrated rate law and also half-life for each 0, first and second order. If you didn't memorize the formula, you are not able to continue to do the calculation. Okay, so based on the question answer here, the integrated rate law for 0 order is shown here. So now continue to the calculation part. You are going to determine the concentration after 10 minutes. That means concentration A is unknown. Rate constant 0.083 is given. The time after 10 minutes is given. Initial concentration 3.5 mole per decimeter cube also given. So substitute all the value in and then press the calculator. You will notice the final answer is 2.67 mole per decimeter cube. Next question, how long? So when we mention of how long here, that means it is referred to the time. Will it take for the concentration A drop to 1 mole per decimeter cube? So again, when we want to calculate the time, either we use the formula of half-life or we use the formula of the integrated rate law. Because from the question here, we have no idea, this reaction may take the concentration become half because initial is 3.5 and then finally is 1. So this is not the concentration, become half. So we cannot use the formula of half-life. So again, we're going to use the integrated rate law. However, this time we have the K value. We didn't have the time. We know the initial concentration and also we know the concentration after a period of time, which is 1 given in the question. So only one unknown is left. So press the calculator, you will get it is 30.1 minutes. Basically, how we know that it is the unit is minute, because in the rate constant here, the unit for the rate constant is per minute, and then over here also 10 minutes. If one of these unit is in second, so you have to convert either to the second or to the minutes. This is tutorial question number 9. The reaction between ethyl ethanol and potassium hydroxide is a second order reaction respect to KOH. The aqueous solution containing equal molar amount of ethyl ethanol and potassium hydroxide were mixed at 298 Kelvin. Initially, the concentration of KOH is 10 mole per decimeter cube. Concentration KOH initial at 300 seconds. The concentration of alkali here refer to the KOH remaining 6.25 mole per decimeter cube. Calculate the rate constant. So maybe we think that we can reuse the rate law, rate equal to the K concentration KOH to the power of 2. So in this question, we cannot use the rate law because we didn't know the order of reaction for the ethyl ethanol, and then at the same time, we also didn't have the concentration of ethyl ethanol. So we cannot apply the rate law. However, we are able to apply the integrated rate law for second order, which is 1 over concentration KOH to the power of concentration of KOH at the time given equal to 1 over initial concentration of KOH plus KT. So concentration remaining after the time, after 300 seconds is 6.25. So you can substitute in 1 over 6.25 equal to initial is 10 plus K we have no idea, and then the T is 300. So by putting in all this value into the calculator, so when you press the calculator, you will notice that the rate constant is 2.0 exponent negative 4. Then the unit for second order, the unit of rate constant for second order is per molar per second. Now let's proceed with question B, calculate the half-life. So the formula for the half-life of second order reaction is half-life equal to 1 over K initial concentration. So maybe some of you will say, if I don't want to put KOH, I want to remain A in the formula, is it okay? Can, no problem. But if you remain A in your formula, you have to write extra one more sentence. Let A equal to KOH. Okay, because previously when we mentioned about A is very general, which is only represent to the reactant. So when you answer the question, you have to specify the A is referred to which reactant, because in certain reaction there is have more than one reactant. Okay, so 1 over K, the K just now we already calculate, which is 2 exponent negative 4. And then the initial concentration given is 10. So press the calculator, you will notice that the final answer is 500 seconds. Okay, in this video, basically, you learn how to determine the order of reaction based on 4 different methods. Either look at the unit of the rate constant, the initial rate law, plot the graph, concentration versus time, or integrated rate law linear graph. And then we also show you a few calculation questions which may involve the formula. So basically, again, the formula that you must memorize in this subtopic is the formula for half-life and also formula for the integrated rate law for 0, first and second order. So these are a few examples for you, a few exercises for you to answer. And then again, we also will discuss during the tutorial time. You can print screen this exercise 1. Okay, this is exercise 2. So before mentioned, just would like to let you know, if in the question you notice that the substance or the reaction is involve the radioactive substance, or which maybe you can see the word nuclear, radioactive substance. So basically you will know that the order of reaction is always first order. This is exercise 3. So like just now we mentioned, when you can see a table with a few of experiment, basically we know that we are going to apply initial rate method. And we also roughly will know the question is asked us to determine order of reaction and then write the rate law. And they can ask us to determine the rate constant. Normally these are in one package. Next, the rate constant is given. So based on the rate constant, you will be able to determine the order of reaction. So try to answer the question A, B, and also C as well. This is the last question that you're going to try to answer. Okay, so that's all for this video. And then with this few exercises, we consider we are complete the chapter 8.1, the rate of reaction. In next video, we are going to continue with the 7.2, which is the collision theory. Thank you for staying with us, and then see you in next video again. Bye.